Hello and welcome to Week 3, Part 1 of EGM702, Using Digital Imagery. The lecture for this week is broken up into 5 parts. We'll start by recovering the basics of digital imagery before discussing different ways that we can manipulate images to make them easier to interpret, from image enhancement techniques to band maths, spectral indices, and finally, image transformation. I've put this slide up because apparently there are people who are unfamiliar with the old ways of film photography, which can cause some confusion when watching TV shows that are set in different eras. I'm hoping that at the very least, you'll learn from this lesson that digital images are still a relatively new development, and that in the past, cameras recorded images on a film rather than in a digital format. Before there were digital cameras, there were film cameras, or, as we used to call them back then, cameras. The basic way that a camera works, which we covered in Week 1, is that light reflecting off of an object enters the camera's lens, which captures the light and focuses it. The image of the object is recorded on a light-sensitive medium, such as photographic film, when that medium is briefly exposed to light by the opening of the camera's shutter. Photographic film is a plastic or paper that is normally coated with a mixture containing silver halide crystals. When exposed to light, these crystals change color. The short amount of time that the film is exposed while the shutter is opened causes a slight reaction in the film. When the film is developed, the confusing process referenced in the previous slide, we have what is called a negative image, shown in the image marked D here. That is, the dark areas of the negative image actually correspond to the brightest parts of the image, marked C, and vice versa. The next step in creating a photograph is to project the negative onto a light-sensitive paper, reversing the process. Bright areas in the photograph then correspond to areas where there is more light or energy that reaches the sensor, while dark areas correspond to where there is less light or less energy reaching the sensor. In other words, the brightness of the image is determined by how much light reflects off of the object being photographed. Modern digital detectors work off of the same idea as photographic film. They still measure the intensity of electromagnetic radiation using something called a charge-coupled device, or CCD, or a complementary metal oxide semiconductor, or CMOS. When exposed to electromagnetic radiation, these sensors create an electric charge that is converted to a voltage that is then recorded by the camera. The amount of the voltage is proportional to the intensity of the energy, again similar to how a photographic film works. These sensors are typically monochromatic, meaning they only record in a single band or a single wavelength range of electromagnetic radiation. Thus, if we want to record on multiple bands, we need to somehow filter or split the incoming radiation into its component wavelengths. On a computer, digital images are typically stored as arrays made up of rows or lines in the y direction and columns, sometimes also called pixels, in the x direction. If we zoom in, we can start to see the individual cells or pixels that make up the image. Each of these cells contains a digital number, or dn. This represents the brightness value recorded by the sensor. Lower values are represented as darker colors, while higher values are represented as lighter colors. The ground sample distance, sometimes called the pixel resolution, is the amount of ground distance that is covered by each pixel. This is measured in both the column, or y, and row, or x direction. For many images, these are the same size, that is, the pixels are square, but it's not always the case. We've talked a bit about the radiometric resolution of sensors, that is, how many possible values the sensor has to represent a range of brightnesses. This was something that you covered back in EGM702. This also translates into how values are stored in digital images. For images, we typically use what are called unsigned integer values, that is, non-negative integers, such as 0, 1, 2, and so on. Similar to radiometric resolution, we refer to an image's color, or bit depth, in other words, how many different values we can use in the image. these values are expressed as a power of 2. So a 1-bit image has 2 to the 1, or 2 possible values. A 2-bit image has 2 to the 2, or 4 possible values, and so on down the line. A computer screen will typically have 3 different 8-bit channels, making a 24-bit image, which allows for over 16 million possible color values. In general, the more values that we use in the image, the more possible values that we have, the better the radiometric resolution of the sensor. As we go up in bit depth, we also typically have larger file sizes and a correspondingly increased need for storage space. This slide shows the same image, but represented using 8 different color depths. You might notice that in the bottom row, the images look fairly identical. This has more to do with the way that the image is represented on the computer screen than the image itself. If we were to look at the gradient of the image, for example, we would see significantly more variation in the 12 or 16-bit image than we do in the 8-bit image. In order to use digital images in a GIS software, we need to have some spatial referencing information that is stored with the image. This typically includes the size of the pixels, or the ground sample distance, the location of the image, or at least the coordinates of one of the corners of the image, normally the upper left corner. We also need to know the way in which the image is being projected, that is, the spatial reference system. Pixel coordinates can be referenced to either the pixel center or one of the corners. Again, this is usually the upper left corner. These different locations are not normally a problem for displaying an image in a GIS, but it can cause problems when you start doing different image manipulations if the software is not properly accounting for the different locations. Many, but not all of the images that you will work with are referenced using a universal transverse Mercator system, as this preserves angles and shapes over small regions, such as within the bounds of most satellite images. In this lesson, we've learned how the images acquired by a sensor, whether using the comparatively ancient technology of photographic film or a digital detector, represent the amount of energy that is seen by the sensor. The properties of the image, its dimensions, its bit depth, are determined by the sensor and how the image is stored. Most of the images we will see are arrays of unsigned or non-negative integers. If we want to use satellite images in a GIS, they need to also be stored with spatial information in order to help locate and project the image. Once again, you can read more about the concepts we've covered in this lesson in your textbooks, Lillesand, Kiefer, and Chipman, Chapter 7, or Tempfley et al., Chapters 4.3 and 4.4. I've also linked to a few different videos that discuss how cameras work and that go over the basics of digital images and how they're stored and represented on a computer. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Thanks. Bye.